Hello, and welcome to another lesson about organic molecules. Hopefully you've been following carefully and now know something about how amazing organic chemistry can be. In the last lesson, we looked at the way that oxygen could be joined onto an organic molecule to make alcohols, carboxylic acids, and esters. In this lesson, we'll look at some other organic molecules made from oxygen, carbon, and hydrogen atoms. We'll discuss the naming of aldehydes and ketones, and once again, we'll look for common patterns in the way these compounds are formed and named. We'll also learn about how oxygen is introduced to organic molecules through oxidation and discuss some of the special physical properties these compounds have. This means that we will have to take a closer look at intermolecular forces in these compounds. By the end of this lesson, you should be able to identify and name carbonyl compounds like aldehydes and ketones. Explain how these molecules form by means of oxidation and describe the intermolecular forces in these molecules and how they affect their physical properties. In the last episode, we saw that the way to identify a carboxylic acid is to look for the oxygen and carbon atoms that are double bonded to one another, and an OH group. We call this the carboxyl group. Now we will be learning about molecules that have a double bond with oxygen but no OH group. This double bond to a single oxygen is called a carbonyl. Compounds which contain the carbonyl group are aldehydes and ketones. The position of the carbonyl in the molecule decides whether it is an aldehyde or a ketone. Let's look at this more closely. When the carbonyl is at the end of a chain, this type of compound is known as an aldehyde. All aldehydes have the carbonyl group at the end of the chain, like this one, which is called propanol. Can you see where the name comes from? We name aldehydes in the same way we name most organic molecules. The 3-carbon chain means that the backbone is propane. The letter E at the end of the word is swapped for Al to show that it is an aldehyde. Easy, isn't it? Now try to draw one of your own. Draw a molecule of butanol. Well, I'm sure you drew a molecule that looks like this. The prefix but indicates that the aldehyde must contain 4 carbon atoms. Remember to place the double-bonded oxygen atom, the carbonyl group, at the end of the molecule's structure, on the first or last carbon. So that's how to draw and name an aldehyde molecule. First, name the backbone, and then end the name with L. Now, what about a ketone? Well, ketones also have a carbonyl group, but the group is inside the molecular structure. Here are a few ketones, and you can see that they all look very similar. Can you see how they differ from aldehydes? Yes, ketones always have the carbonyl inside the chain, unlike aldehydes that have the carbonyl on the last or first carbon atom in the backbone. By now, I'm sure that you've picked up that the molecules in a homologous series are named by finding the name of the backbone molecule first. Thereafter, the name changes according to the functional group that we find. Ketones are no different. Let's take a look at the simplest ketone and see if we can name it. This compound has a carbon atom chain with 3 atoms in it. The backbone is therefore propane. Because there is a carbonyl functional group inside the chain, this is a ketone. When there is an oxygen-containing functional group in a molecule, we change the end of the word to name it. Ketones are no different. The end of the word changes from E to O-N-E, so propane becomes propanone. Now, I'd like you to name one on your own. Think about all the naming rules you know and try to apply them. Can you name this molecule? It is definitely a ketone, and it has 5 carbon atoms in it, so it is a pentanone. The tricky part is to name this molecule based on the exact position of the carbonyl functional group, just like we did when naming haloalkanes and the double bond in alkenes. Remember, the first step is to number the carbon atoms in the backbone, starting at the end that is closest to the carbonyl group. So in this molecule, the carbonyl group is on carbon number 2, and so the full name is pentan 2,1. One thing we have not paid much attention to yet is how we can make these carbonyl compounds. There are many carbonyls in nature, but if we wish to get chemistry to work for us, we have to find ways to make the chemicals that are useful in very large quantities. Let's start in the lab and see if Philip can make some aldehydes and ketones there.
Hi all of you. Today we'll see how we can make aldehydes and ketones from alcohols. I'd like to show you the reactions of the 2 alcohols I'll be using. It's easy to see how we can get aldehydes and ketones from alcohols. Alcohols with the hydroxyl group on the last or first carbon atom of the chain are called primary alcohols, like butane-1-ol. When the hydroxyl group of the alcohol is at the end of the chain, like here, we can make an aldehyde very easily. One hydrogen atom comes off, and a double bond forms between this oxygen and carbon. We'll be using acidified potassium dichromate as the oxidizing agent. When the reaction happens, it changes from orange into green, showing us that a reaction is taking place. Let's add the potassium dichromate solution to the alcohol, which we have stirring here, and see if we get a reaction. Notice how the color changes very quickly when we add the potassium dichromate to the solution. This shows us that the reaction is indeed happening. So we can see that primary alcohols can be oxidized to make aldehydes. What about other alcohols? In the same way, we can oxidize alcohols with the OH group on one of the carbon atoms inside the chain. These are called secondary alcohols. We can also oxidize these, but the product will be a ketone and not an aldehyde. Again, we'll use potassium dichromate to see if oxidation occurs. I'm adding potassium dichromate to butane-2-ol. This reaction is slightly slower than the last reaction. The orange color does not change to green as quickly for the primary alcohol we used. Can you think why this might be? The oxidation of a secondary alcohol into a ketone is slow. The carbon atom that is being oxidized is in the middle of the molecule. When we oxidize a primary alcohol, the reaction is quicker. This is because the carbon atom at the end is being oxidized, so it's much easier to reach and react with the oxidizing agent. Wondering why scientists go through all this bother to make aldehydes and ketones? Manufactured aldehydes and ketones are used in many interesting ways. To preserve species in museums and labs, to manufacture many plastics and glues, to process leather and make the silver parts of mirrors, to make nail polish remover, varnishes and paint strippers, and to make many other chemicals, like acetic acids and acetate. Some aldehydes and many ketones have pleasant smells and can be used to flavor foodstuffs and as ingredients in perfume. Some of the flavors available are almond, spearmint, caraway seed, licorice, lemon, cinnamon, pineapple, strawberry, ginger, and even butter flavor. Some even smell of wood, leather, or lavender. I hope you've enjoyed making aldehydes and ketones with me. Organic chemistry really is a lot of fun. I think you're going to learn some more about aldehydes and ketones now.
Gosh, I thought I was getting real fruit in the flavored water I drink. Now I know better. Well, by now we know how to name organic compounds that contain oxygen and how they are made. I'd like us to learn about some of their physical properties now. Compare the boiling points of these isomers. We can see that something strange stands out. The two molecules consist of exactly the same atoms and have the same formula and molecular mass. But we can see that the boiling points are very different. See, it will take more energy to boil propanoic acid than to boil ethyl methanoate. Boiling a molecule weakens the forces of attraction between molecules. So if the boiling point is higher, it means that the forces of attraction between the molecules are stronger. Let's look at molecules containing a hydroxyl group. It seems that these molecules must have strong forces of attraction because of their high boiling points. Look carefully at this model of the propanoic acid molecule. The gray spheres represent carbon atoms. The red ones represent oxygen atoms, while the white spheres represent hydrogen atoms. Notice that at the end of this molecule, we have hydrogen directly bonded onto an oxygen atom to form the hydroxyl group. Oxygen is more electronegative than hydrogen and does not share the bonding pair of electrons equally. So a partial negative charge forms on the oxygen atom, and a partial positive charge forms on the hydrogen. This means that this molecule is not nonpolar like the hydrocarbons, but is polar. Can you see what this means for the forces of attraction? The positive hydrogen end of the molecule is attracted to the negatively charged oxygen end of a different molecule. These electrostatic forces of attraction between molecules are very strong. When chemists first discovered them, they thought they were a new type of chemical bond and called them hydrogen bonds. But we now know that they are not really chemical bonds in which electrons are shared, but they are a special type of intermolecular force. In propanoic acid, hydrogen bonds form between the negative oxygen pole and the positive hydrogen pole of different molecules. More energy is required to break these strong hydrogen bonds, and so the boiling and melting points of molecules, like propanoic acid, that have a hydroxyl group are higher than other isomers that don't have hydroxyl groups. So what happens between molecules that have a carbonyl group? Notice the boiling point of the ester ethyl methanoate is 54 degrees. So at room temperature, this is a liquid. So there are intermolecular forces holding these molecules together. But notice, there are no hydrogen atoms joined directly onto the oxygen atoms. The oxygen atoms will still form a slightly negative end, and the carbon will be slightly positive. But no hydrogen bonds form. The intermolecular forces are weaker van der Waals forces, and a small amount of energy can separate these molecules. So the boiling point of ethyl methanoate is lower than propanoic acid. Now let us see if the position of the hydrogen bonding partners on a molecule affects the boiling points of the molecules. Look at these alcohols. They are also isomers, so their molecular mass does not play a role. Can you see any pattern in their boiling points? Can you see that when the hydroxyl is surrounded by more carbon atoms, the boiling point is lower? With many carbon atoms around or nearby, it is difficult for other molecules to reach and form hydrogen bonding. And when there is little hydrogen bonding, the boiling point of a molecule is always lower. Here, the hydroxyl is surrounded by or close to 2 carbons, and its boiling point is just over 117 degrees Celsius. While here we see 3 carbons in the vicinity of the hydroxyl. This molecule boils at 99 degrees, which is lower than the previous one. And this molecule, with 4 carbons close to the hydroxyl group, has the lowest boiling point at 82 degrees Celsius. So the trend seems to be that when the hydroxyl group is surrounded by many carbon atoms, the boiling point is lower. This is because it is difficult for other molecules to reach and form hydrogen bonding with the OH groups. And so, with fewer hydrogen bonds, such molecules have lower boiling points. In closing, let's do a task relating to molecular structure and boiling points. The molecules are isomers, so look at their structures for clues. 1. Name these 2 molecules, and 2. State which one has the lower boiling point. For more information on organic molecules and related topics, please visit our website on www.mindset.co.za/learn.